Well, greetings, Mr. Kolazar's class. We're going to start out the second section of kinetic molecular theory when it applies to solids, liquids, and gases to focus just on the idea of liquids. And so we're going to look at that, have a little bit of range of motion. They're not easily compressed. They're kind of touching each other, but what's going on to make things liquids? And then from there, we're going to focus on this idea of what viscosity is when it comes to liquids. So kinetic molecular theory, the KMT, developed to explain ideas about gases, but now we're going to have it focus on those liquids and solids with those intermolecular forces and what's going on there. So first off with our KMT's particle size. Particles, remember, very small, and now they're very close together, so they do experience some attractive and repulsive forces between them. So remember, for liquids, they're able to move and slosh kind of around, but they're going to be continually in constant motion, but able to move past each other touching. Particles, constant random motion, collide frequently because they are close together. Now remember, from particle energy, particles have kinetic energy because they are moving, so we get that kinetic energy from them. Measure with temperature. The faster they're moving, the higher the temperature. The slower they're moving, the lower that temperature. So that's going to affect our next part, that intermolecular forces. So behaviors of those fluids, remember, they're more dense than gases. Particles are close together, so mass is more influential. So they have more mass, the same mass, but a less volume. If they've got less volume, that increases the density. They're more dense than gases are, so liquids more dense. Uh, our key one we're going to talk about coming up now, ability to flow and diffuse. So a fluid can be either a liquid or a gas, are both fluids because they have the ability to flow and diffuse. So we usually think about just liquids being fluids. That's one we're going to focus on, but gases also are fluids and the idea of fluid dynamics. So our key one, viscosity. So viscosity is going to be the measure resistance to the flow of liquid. So the slower it flows, the higher the viscosity. So I want you to write this one down at the bottom. Let's write this one in. Higher viscosity, the slower it flows. So the kind of the thicker it is, the more it resists wanting to flow. It's going to be determined by the strengths of the IMFs, the size of the particle shape, and the temperature of material, all determine how that liquid flows. The slower it flows, the higher the viscosity. So our first one, example-wise, strong IMFs, higher viscosity, poor fluidity or poor flowing. Weak IMFs, lower viscosity, better fluidity. So like strong IMFs, it could be like chocolate syrup. Would be an example of a high viscosity, where like oil would be an example of a low viscosity. Flows much easier. Maybe water would be an example of a low viscosity. They flow very easily. Chocolate syrup, honey could be another example where we're looking at something that has a higher viscosity versus lower viscosity, the ability for it to flow or pour. Stronger IMFs, the less it wants to flow. Temperature-wise, high temperatures, particles are moving faster, they overcome those attractive forces, are less viscous. So low, slower moving, don't overcome those attractive forces, more viscous. So example could be like hot nacho cheese, cheese versus cold nacho cheese. So when we think about those two, fast moving, it flows nice and easy, and then this is much slower pouring when it goes. So hot versus cold would be a big difference there on being able to actually flow. So viscosity by temperature. We could also look at viscosity. Larger particles would flow slower, more viscous. Smaller particles able to move around each other, move faster, would be less viscous. And we could even get into the shape of particles. Long particles stick together more. more viscous, or shorter, smaller particles don't stick together as much, would be a less viscous substance as we're going there. So those would be other ones to look into, how well that ability for that liquid to flow is. Another thing we want to look at today is surface tension. Surface tension, the energy required to increase the surface of a liquid, measures the inward pull of the particles. It's basically, I like this last one here, it's going to be to add in the strength of the surface of a liquid. So one challenge we have is to float a paperclip on water and how that's able to be done. Or like how insects or little water bugs can float on the water. Surfactants are going to be known as surface acting agents. So where that name surfactant comes from, it's basically the fancy name for a soap or detergent. Helps lower the surface tension of the water, makes it easier to remove dirt and stains by breaking that surface tension down. So look at this cohesion, force of attraction between identical molecules, the reason for surface tension. So we're actually able to get that strength of that water wanting to hold itself together, causing that paperclip to float on top. Adhesion, force of attraction between molecules that are different, reason for meniscus and capillary action. Adhesion, a good example of that would be tape, would be another one there. Cohesion or meniscus is that curved liquid because the water actually wants to stick to the side of the metal or the glass column. So it actually is sticking to that side, causing that water to curve up because it wants to attract to the glass. Capillary action results in that pulling up of the blood from that capillary, wanting to attract to that material in that tube there. So adhesion versus cohesion there. Uh, Volatility, ease at which liquids evaporate, relationship between IMFs and their strength of holding together. So, if you have a container of liquid, how easily does that liquid want to become a gas? Is the idea of volatility. So the stronger the IMFs, the less it wants to evaporate or become a gas. Kind of a couple little fun demos. We actually stuck some paper clips on the surface of water using that surface tension, and then by adding a little bit of soap, broke that surface tension and caused those paper clips to come to a tumbling or fall to the bottom. And again, we've got some paper clips floating on the surface. Idea when we put the soap in, the water wants to keep the attraction, so they're actually sliding over until that surface acting agent, that soap, actually takes over and breaks that surface tension in that second one. So both those cases, that water and that surface tension. We'll continue on with this, but safe travels to everyone today.